Oh, you don't know this, do you? No. Well, except for the class this morning, all my lessons are recorded. What is recorded is the screen and the audio. I thought you signed up to my YouTube channel, didn't you?
I subscribed.
I didn't watch anything, I see. Well, anyway, all of these are put on YouTube, so you can see and hear everything that was done in class. Okay, let's continue. So, next lesson, Newton's 3 laws. See, you don't get that in biology, do you? No? No, you don't. Your friend, what's the other Malaysian student who wants to study actuarial science? Is he staying in biology? Really? Okay.
He said he's going to make it harder to him.
Okay. Alright, Newton's 3 laws. Now, earlier in the week we had a look at one of these laws already. Which one did we do earlier in the week? Second law. Okay, so we're going to have a look at all 3 now. Okay. Right, so does anybody know Newton's first law? Yeah, so what would it be as a sentence? Nearly perfect. You just forgot one word in your definition. You almost have it perfect. You said state of motion, but a very special type of motion, not just any state of motion. Closer. Not just a straight line. No. Uniform linear motion. That was the only thing you were missing, was the word uniform. So Newton's first law states, if a body's at rest, it remains at rest, or if it's in motion, it moves with uniform velocity until it is acted on by a force. So basically it will keep moving at a uniform rate or not move until a force acts on it. Now, for exam purposes, you do not need to match it word for word, okay? So like the way you said it, it's fine. When I'm marking it, I'm looking for key words. So key words would be uniform, would be rest, would be, acted on by force. Like these are the key things I would look for in the definition. So you do not need to match this word for word. Got that? Yeah. You've seen this before? Did you say it a similar way in school?
I think so.
Okay. Continue? Yeah. Here's a good picture of the meaning of the first law. So for example, an object at rest will remain at rest unless it's acted on by a force, a resultant force, or unbalanced force. And then also the law says an object will move in motion with a constant speed unless acted on by a force. Now, of course, in real life things are more complicated than as this, because although this is moving, there are actually many forces acting on it. For example, gravity for one, but also the drag. Yeah. So Newton's first law in real life, it's kind of hard to see it actually happen because there's forces acting on everything all of the time. I think the only one that really can be true all the time is this one. But when anything's moving, there's always a force acting on it in real life. Okay, so that's the first law. Now the second law, you know this already. What is the second law? Yep. Force equals? Yeah. Yes, yeah, just simply that then. How would you put this as a sentence? You know, in the exam you can't really just write F equals MA, so if you were to pull this out as a full sentence, what would you say? You know, you're pretty close. Go on, give me a full sentence. With a verb and everything. What would it be? Perfect. Force is the product of mass and acceleration. Product is another word for multiply. Okay. Simply F equals MA. And finally the third law, that's just a picture there. The third law is the one about the reaction. So it basically says that for every action there's an equal and opposite reaction then, yeah. Or, as I put it, you do something and something happens. Got that? Yeah. Continue? Yep. Here's a simple example of it. The action of the air coming out of the back of the balloon will have a reaction of the balloon moving forward. It's very simple, but actually this will be a very useful example later in the chapter. Okay, so this is just a simple example of an action and a reaction. There is other uses of the third law for now, which is more important, which is this type of diagram, which you probably have seen before here. This force here, what's this one in the blue? The gravity, the weight. Now you realise that if I put something on the table and there's a weight acting on it, it should move down, but it's not moving down. So there must be a force acting against the weight to cancel it. And for these diagrams we call that green force. Yeah, so you could actually call it resistance, but there's another word for it. Reaction, yeah. Resistance is usually used in the context of like friction. But when it's stationary because of a surface, we use the word reaction. Although their meaning is kind of similar, it's an opposing force. So, the reaction force is the force provided by the reacting object, in this case the table. This is an example of Newton's third law. I should tell you that the biology teacher doesn't believe that Newton's third law exists. I just, I feel I should tell you this. Has he told you this in class? No, you didn't get to that lesson yet. He doesn't like this example, but it's a real example. So, right now, if I push against the wall, I'm applying a force, but I don't move. So what do I know that the wall is doing? The wall is pushing back. Now when I say pushing back, I really mean there's a force coming out of the wall, as if the wall is a person pushing outwards. But this force only exists to stop me. As soon as I remove my hand, this force then is gone. Okay. So these are called reaction forces. Now, if I push hard enough, you could have a force greater than the reaction force, and what would happen then? You go through the wall, exactly. And I do that from time to time. Okay, continuing. Yes?
But I don't get like why doesn't he like this?
He doesn't believe that the wall could be pushing back as if it was alive. You know what I mean? Yeah. Yeah. He has trouble accepting this problem. Okay. Continue. Yep. So, here's our first simple example. I think you should be able to do this one. The key is to remember that these must balance. Okay? So you have a 20 kilogram block on table. What is the reaction force? Okay, just take a few seconds to calculate that, please. The picture is just like this. This is the picture. So just take your calculators out and try and get this for me if you can. Yeah? And what does W equal? Yeah, what's the formula? mg, which in this case would be 20 times 9.81. What did you get? 196.2 newtons. Okay, that's fine. That's fine. They get harder though. A block of mass 200 kilograms is at rest on a table. A man tries to lift the block vertically upwards by using a rope. He pulls with 1,000 newtons, but the block doesn't move. What is the reaction force? So I'll just draw the picture here. It's kind of the same picture. You have your block, you have your weight, you have your reaction force, but also you have the man pulling up with a force of 1,000 newtons. And the mass here is 200 kilograms. Okay, so again, I'll give you a minute. I want the reaction force. And remember, the block is not moving. We have answers?
You want the reaction force
Mhm.
without the mass force?
Oh no, you need to consider it. Sounds about right, yeah. Okay. Newton's first law says if this is not moving, then everything must be balanced. So it must be the case that 1,000 plus or equals the weight from Newton's first law. So we have the or is equal to the weight minus 1,000, which is equal to mg minus 1,000. So let's see what that is. You have it, yeah? I think this is what you said, 962 newtons. Yeah? Is that okay down the back there? Yeah. Let's see. Okay, let me give you another one to try. This time it's the same story, except he pulls at an angle of 45 degrees. So I'll draw it here for you. Here is the block. Again, it's 200 kilograms. And he's pulling it here at an angle of 45 degrees, and it's still 1,000 newtons. Yeah, what's wrong? Yeah. No, if you have a question, go ask, no problem. There's the reaction here. There's the weight here, and I didn't say it in the question, but I meant to say it. The block moves at a constant speed. Okay, so again, my question is, what is the or? And I'll remind you that you should resolve here into this direction and into this direction. Okay, so I'll give you a minute to try this one now. Wow. In fact, actually, no, I'm sorry, you don't need to know it's a constant speed. I take that back. I don't need to tell you that to find the ore. The only thing you need to know is that the block stays on the ground, that it doesn't go off the ground. What answer did you get?
1,254.9.
Yeah. Yeah, it should be a bit bigger than the previous answer. Okay, so here, this one is 1,000 cosine? Yeah. Which is 1 over root 2, and this one is 1,000 cos, which is 1 over root 2. So again, because it's not moving vertically, we can say or plus 1,000 over root 2 equals W, which is mg. So if I just take that over there, let's have a look at what we get. 200 times 9.81 minus 1,000 over root 2. 1255 about newtons. Okay. Now, let's see. A block of mass 73 kilograms is at rest on a rough table. So rough means there's friction. A man is dragging the block behind him with a rope. The rope makes an angle of 45 degrees with the ground, and he's pulling on the rope with a force of 1,000 newtons. The block moves at a constant speed. What is the friction force? What is the reaction force? Okay, try this one now. You have answers, yeah? And down the back? You have answers? Yeah. Let's have a look and see. First, let me just draw the picture. This is 73 kilograms. He pulls at an angle of 45 degrees, and that's 1,000 newtons. So this one here would be 1,000 over root 2, and this one here would be 1,000 over root 2. There's also a friction force here, I'll call that just D. There's a reaction force here, I'll call that R, and then there's the weight force here, which is mg. In this case, it will be 73 times 9.81. Now, because it's moving at a constant speed, Newton's first law says that the R plus 1,000 over root 2 should equal 73g, and the 1,000 over root 2 should equal the friction, yeah, the d, yeah. That's all okay, isn't it? Yeah. So this must equal this, and these two must equal this. Alright, so if you've typed that in for me, what did you get for or, and then what did you get for D? D is 707 newtons, we'll just 707, and then the or 9 point, oh, very small reaction force, newtons. Yeah, okay. Can I continue, or do you need to write this down? Yeah. Yeah, no problem. Down the back, this one was okay for you? Yeah. Okay, continue? Yeah. Okay, I think this is my last example, but it's a tough one. It's a real tough one. Let's see if anybody can do this. A weighing scale really measures reaction rather than weight. So what I mean by that is, when you stand on a weighing scale, you think what it's telling you is your weight. It's not. What it's telling you is not your weight, but your reaction force. Now you might be thinking, what's the difference? Because in this picture here, or equals W. So in this picture here, it doesn't matter. If they give you the or, it's the same as giving you the W, right? But now, the weighing scale is then lifted vertically up in the air with an acceleration of 1. So in other words, maybe this is in a lift, and the lift heads upwards with an acceleration of 1 meter per second squared. Would the reading increase or decrease? What do you think would happen? Would it get bigger or smaller here? Like, think about, it increase. Think about when you're in an elevator and the elevator moves up. Do you feel lighter or do you feel heavier? You feel heavier. No, you're not really heavier. You didn't suddenly gain weight, okay? So, this one's a bit of a, you really have to think about this one. I want to know, it's not, well in this example it's not a person, it's a book. So there's a book placed on it and it has a mass of 0.5 kilograms. I want to know what the weighing scales would say its mass is if it moves upwards with this acceleration. It's a bit tricky, you'll have to think about this. You look confused. Yeah. What is the weight? What do you mean?
Oh, you mean like to find the weight?
In other words, I place a book on a weighing scale, and the weighing scale says it's 0.5 kilogram. But then the elevator moves up, and I want to know what will it say now. So you understand that, of course, it will say it's more than 0.5 kilogram if it's moving up. My question is, what will it say? Yeah, think good and hard about this one. You got an answer? Show me what you got.
About 0.555.
Sounds believable. Could be right. Could be. Anyone else? What do you think? You look so confused. Yeah. No problems? Let's have a look now. This one is a bit tricky if you don't figure out the idea. So let's have a look at this now. At the beginning, before it moves, it's like this. Oops. And I placed the book here. I'll just draw this as the book. And this is half a kilogram. So there's a downward force of 0.5 G, and there's an upward force of 0.5 G. They're balanced at the beginning. What is this? 4.905 newtons, isn't it? So I'll just write it like that. This is 4.905 newtons, and this one here is 4.905 newtons. And the weighing scales, it looks at the reaction force, does a calculation, and says this is a 0.5 kilogram book using this number here. How it does that is not important. It basically just uses the formula W equals mg to convert the force into a mass. But now in this picture, we'll say it's X, and we don't know what it is, although it's still half a kilogram book. If it's accelerating upwards, which force is greater acting on the book? Its weight or the reaction provided by the weighing scales? Which is greater? Yeah, the ore is greater. In fact, what is the total force? The total force would be upwards or minus W. That's the total force upwards. This will be a little bit bigger than this. Because it has to move up, it must be bigger than the W. If it was smaller, it would move down, and if it was equal, it wouldn't move. So the ore is bigger than the W because it moves up. How much bigger? We'll call that F. But we have a formula for knowing what the total F is. What's the formula for knowing the total F? MA. Now, do we know the M? We do. And do we know the A? We do. And do we know the weight? What's the formula for the weight? mg. So ore minus mg equals ma. So ore equals mg plus ma. 4.905 plus 1, that is 5.905 newtons. Right? Yeah? Oh, no, sorry, that's wrong. I meant to say plus 0.5, because that's a 1. That's 0.5 and that's a 1. So that would be 5.405 newtons. Now that's not me finished, because I didn't want the reaction force, I wanted the weight. So in this picture the reaction force is 5.405 newtons. Now if you compare these, how much bigger is it? Let's see. 5.405 divided by 4.905. Yeah, so what I can say is that this is 10.19% more. If the reaction force is 10% greater, then the weighing scales will think the mass is 10% greater. So instead of thinking it's half a kilogram, it will think it's now 550 grams. It thinks the mass is 0.551 kilograms. Yeah. You got this? But I wonder if you did it similar to me or a different way.
Take that 5.45 divide 9.81.
Yeah, that's fine too, and divide by 9 point. That's what the weighing scale actually does when it calculates it for you. It takes this and divides it by 9.81, and you'll also get this. Tricky. But what I like about this is it makes sure you understand what's happening here. This is kind of the key step. That's the key step. Okay, since a few of you had trouble, make sure you write this down carefully. Oh, you need to email me because I need to change your Moodle page. So, can you just remember sometime today to email me so I can do this for you? I need to know just your username that you use to log in. You have that? Yeah.
Where is the final answer?
Sorry, it's this here. Okay, continue. Yeah, I think that was the last example. It was, yeah. Alright, so what we'll do now is you have two worksheets to work on. The projectiles, which some questions are quite hard, and this lesson, I don't know. The projectiles is probably harder than this. I think the only really hard example was this one. Yeah. So I'd like you to work on both of those worksheets now, and then tomorrow we have the tutorial. So if there's any questions you can't do from the book, we'll do those tomorrow. But have a start on those two worksheets for today now.